Welcome back. In this brief lecture, we will address some of the issues that go into the design of a fuel cell. Typically, a design is done in a particular context. In this case, the context is provided by application of fuel cell to space. Before we start the design, we are provided with the polarization curve of a particular fuel cell. We have addressed these issues on polarization curve in many of the previous lectures. Please look into that. So you need to know what is the potential you may get from the fuel cell as the current density is increased. In every engineering context, certain thing is a premium. In the context of space, weight is a premium. So decreasing the weight is critical for any space application. So the design will have to meet the requirement without increasing the weight significantly. And what kind of requirement um, is required? So typically, these are provided based on the context. For example, in this context, power is very critical. Fuel cell supplies the power to different equipments. The length of the machine is very important. Mechanical efficiency, fuel efficiency have been defined in previous lectures. A fuel cell with a specific mechanical efficiency, fuel efficiency, and utilization of hydrogen is also fixed. The power conversion efficiency is further fixed. Oxygen utilization is also fixed. The cell pitch provides an indication on the spatial dimension of the fuel cell. The number of fuel cells present in per unit distance is provided by the cell pitch. The area of the electrode is also specified. The density of the fuel cell stack is also specified. And besides the fuel cell electrolyte and electrode, there are other components which add to the weight of the fuel cell stack that is specified by this quantity. So once these things are specified, we can get to the mass of hydrogen that is required to meet the power requirement. This formula has been elaborated in a previous lecture. Please look at that lecture to get an idea of how this formula was derived. But what is important to note is that the mass of hydrogen fuel that is to be utilized is inversely proportional to the voltage. If voltage increases, the mass is brought down. Once you know the mass of hydrogen, it automatically fixes the mass of oxygen that is being utilized. And the power of the fuel cell can also be obtained. All these things have been clarified in some previous lectures. So the volume of the stack can also be known once this ratio, that is the active area of the electrode to the overall area of the stack, is known, and the fuel cell pitch, the pitch of the stack. Once these things are known, the mass of the fuel cell stack can be obtained. That is determined by the volume of the stack times the density and the other factors besides the fuel cell stack that add to the mass. So once this is known, we can get the overall mass. The overall mass is sum of three quantities: the mass of the fuel cell stack, mass of the fuel, and the mass of the oxidant. So all these things goes into obtaining the mass, and then the central feature is here. As I've stated many times in the past, Much of engineering is about understanding the trade off. As you increase something, for example, in this case, we are increasing the voltage that can be obtained from the fuel cell. As you increase the voltage, the mass of hydrogen and oxygen comes down more or less in a linear manner. But the there are other things like the mass of fuel cell stack, which vary in a non-linear manner. So the total mass of the fuel cell stack and the mass of oxidant and the fuel is shown here. This kind of relationship, a quantitative relationship of important design requirement. For example, here, um, mass is a design requirement. As you vary the cell potential, the total mass varies in this manner. So while you increase the voltage, the mass is coming down, but beyond a particular point, the mass increases dramatically. So whenever there is a minima or a maxima, whenever there's an extrema, it is a competition between two particular features. One is here, in this case, the decrease in the mass of fuel and the oxidant, and other is what happens when with the um, e- uh, fuel cell, the mass of the fuel cell stack. So the sum total is being plotted here. So if you want to have the least mass, you want to be staying somewhere in this region. You do not uh, want to be in this region or in this region. So this is the typical way uh, a fuel cell stack is designed uh, for in a particular context. Because mass is premium for space application, we looked at the mass while varying a particular important feature of the fuel cell. So in different contexts, for example, similar kind of analysis can also be done in the context of electric vehicles, but where again mass is an important quantity. But in some cases, for example, if you're installing a fuel cell or a battery for um, in an army station at high altitude, the duration might be an important design feature. So depending upon the engineering um, context, the quantity that has to be optimized is varied. In this context, mass is being optimized. Oh, in overall, in the series of lectures, we have looked at different aspect that goes into the analysis of fuel cell stack and systems. In all these topics, what is given is the polarization curve. Once this is known, we start the design. We looked at different configuration, and we broadly classified the configuration into monopolar design and the bipolar design. We also looked at different aspects of oxidant and fuel utilization. All these things involve trade-off. Analyzing the trade-off is an important part of engineering. That is why a quantitative description is always useful. We also looked at different aspects of machining, uh, flow fields, different aspects of water and temperature management in the context of solid oxide fuel cell, and PEM fuel cell was also addressed. This is an aspect which is getting increasing attention. The electrochemomechanical coupling that goes into batteries and fuel cell. And in this lecture, we looked at a case study in the context of fuel cell for space application. Thank you.